So good afternoon, everybody. My name is Doeland. I'm one of the structures experts at EASA, and I'll be co-sharing this presentation with one of my colleagues, Laurent Pinsard. So we're going to focus. Oh, that was not the intention. Sorry. So here we're going to focus on structures and modeling and simulation. So we're moving a little bit away from all the other presentations you had earlier today in terms of flight test and systems. But I think you will see throughout the presentation that many of the elements that we're going to present will probably appeal to you. You'll recognize it, although we may use some slightly different terms in the structures area. But even though you may not be a structures expert or have a structures background, I hope you can still relate to this presentation. So like I said, I'll be co-presenting this with Laurent. I'll take care of the first part. So I'll talk about the background and the context first, and then I'll introduce the concept of what I call a credibility assurance framework. Then Laurent takes over and he will translate everything I tell into the Rotorcraft world, and we'll end up with a summary and conclusion. So there are a lot of buzzwords and terms flying around. Certification by simulation, certification by analysis, it's a very popular one, virtual certification. All of these terms are not really well defined, but I think in general people mean increased usage of advanced analysis and a reduction of physical testing. And again, that would apply to structures, but that happens also in the flight test or in the systems world. Some of these terms are a bit misleading, I think. Certification by analysis, I particularly don't like because it gives the impression you can do everything by analysis. And testing is a thing of the past. Well, that's definitely not true. And that's what we'll try to point out during the presentation as well. To be a little bit more objective and neutral, we use the word modeling and simulation throughout this presentation. It's a bit, like I said, a bit more neutral, but it's a computational means to, let's say, simulate a particular physical phenomena. That's basically what it means. And modeling is then, of course, creating the model, and the simulation part is running the model, getting some results and analyzing the results. However, even modeling and simulation is already covering a lot of different things to a lot of different people. So in the scope of this presentation, we really try to focus on, well, first of all, what we call the certification qualification phase. So here we're not talking about what happens in the development phase of a rotorcraft or an aircraft. There, modeling and simulation is also used very extensively, as you probably know. That's what we're going to talk about today. We're also not talking about what happens in service, and here you can think about digital twins, structural health monitoring, whatever. Again, that's outside the scope of this presentation. We're really looking at the certification phase here. Secondly, obviously, we're focusing here on structures, but within structures community, we also have a lot of different flavors. We have solid mechanics, which is more static and fatigue. We have structural dynamics, which is more crashworthiness, bird strike. And we have the fluid dynamics, which is more related, obviously, to the load and the flutter issues that we have. To make things even more complicated, we also have different behaviors, linear, nonlinear, static, dynamic. And we have different numerical techniques to address all these phenomena in terms of discretization, in terms of meshing, so breaking down the structure in different pieces to make the analysis feasible. And we not only worry about the solution process, but also the pre-processing and the post-processing. So even within the scope of this presentation, it's already quite a complex set of activities. Now, of course, a picture always tells more than 1,000 words. So here are some of the things that I mentioned on the previous slide. I copied these rather randomly from the internet, so I hope I'm not violating any copyright issues here. But you'll see. Let's see if this works. Yep. Okay. So you see static strength, you see bird impact, bird strike, fuel tank, drop test, ditching, and dynamic seat testing. And these are just a few of the examples that I mentioned on the previous slide. And Laurent will go a little bit in more detail in his part of the presentation. So what we see in the structures community, and not only there, it's also happening in other disciplines, and it's also happening outside aerospace. We know that there is an increased usage of what I said, advanced analytical means, often accompanied by a reduction of physical testing. That's a trend that is definitely there. Now, when it comes to showing of compliance, you probably know that there has always been this mix of test and analysis. If you take a look at 29307, which is proof of structures, one of the key requirements in the structures build, it clearly says that you can show compliance by test only. That's an option. It's not very often used because it's quite complex to do that, to build a specimen and to apply all the critical cases. That's quite a challenge. So in reality, you will see that compliance is shown by a mix of test and analysis. So that is not new, but what is new is that the balance is shifting towards more analysis and less testing, less physical testing. So from a safety point of view, we're not opposed against that trend. In fact, we see the benefit. We think that if you use modeling and simulation techniques properly, then you can have a lot of benefit, not only from a, let's say, economical point of view, a better or more optimized design in the end, but you can also build a safer product simply because you can investigate much more conditions analytically than you can ever do by physical testing. So we definitely encourage the trend as such, but, and I said, if you use modeling and simulation techniques properly, the key concern is always the credibility, or some people call it trustworthiness. And earlier this afternoon, I heard the term fidelity. So people have different mindsets on that. But in the end, it's the big question. Nice color pictures, like the ones I showed on the previous slide, but what do they really mean? Can I trust the results? How credible are they? So when it comes to credibility, we have developed this, what we call credibility assurance framework. It's not something that we at EASA have invented. If you're a little bit familiar in this world, you immediately recognize all the terms. So we didn't invent anything new. It's a reflection of what's already out there. So going through the elements, starting with verification on the left upper corner, and then going clockwise. The first element we have is verification, and that is both code and solution verification. So code verification is really about showing that your code, the software tool you're using, is free from errors and bugs, well, as much as possible. But also that the algorithms, the governing equations that you have programmed work correctly. Solution verification has everything to do with the quality of the model that you build, the assumptions you make, the meshing, the mesh quality, the mesh conversions, but also the numerical errors that you introduce by doing this simulation, just to name a few examples. The next one is validation, and that is probably what you're familiar with. So you have test data, you have analytical results, you're trying to compare the two, which sounds easy, but it can be quite tricky. First of all, you need to agree, how do you compare things? If it's two numbers, it's relatively easy. If it's a time signal that you want to compare, it's already more complicated. And then the next question is, what do I accept? Do I accept 3%, 5%, 10%? As already pointed out, there are no hard and fast criteria in many cases. Extrapolation, the next element, is where you have a validated model, you're comfortable with what you're doing analytically, but you want to, I have to stop doing this, you have to want to extrapolate it, you want to raise the design weight of your rotorcraft, you want to maybe lengthen the fuselage of your aircraft. So you want to show compliance by analytical means based on the validation domain that you have established before. And errors and uncertainties. And that's where it becomes complicated, because I just said for validation, you're comparing two things, but you're not comparing two things, you're comparing two ranges, because your test data and your analytical results will have margins that have errors, uncertainties. So how you start comparing these things is also quite a challenge. But you have to take care of that. So those first elements the first four that I just mentioned, are often indicated as VVUQ, verification, validation, uncertainty, quantification. But there's more to credibility, and that's the last two elements shown on this slide. And that's the experience. And I think we all agree that experience is extremely important when you do modeling and simulation. Both at the individual level, the staff, how they are trained, how they are qualified, how they are supervised and peer reviewed, but also at an organizational level. How do you make sure that you have the right people employed, and how do you keep them current? And the last element here on the slide is what I call governance, and that has to do with data management. So you're developing your models. It's an iterative process, so configuration management is important. And you also want to make sure that what you have and what you store is still usable 30 years from now when your Rotorcraft is still in service, and you may have to go back to your analysis. So these are just some of the challenges that you may have if you go into the modeling and simulation world. So, like I said, there's always this mix of test and analysis in the showing of compliance. And up until now, and I think also in the foreseeable future, there's a lot of emphasis in the structured community, but I think outside as well, on test data. And that has always been, let's say, our bread and butter of certification. Okay, you've done an analysis, and with typical question we ask you, show us the test data to validate your analysis. But like I said, this balance is shifting. We see more and more advanced and complicated analysis, less test data to make the correlation. So we need a new strategy. We need to spend more time on making sure that the modeling and simulation that is done is credible. So the quality of the modeling and simulation is becoming more important. Something I have to admit, we as regulators have not paid a lot of attention to in the past. Again, because we were in the comfortable position, we had a lot of test data to correlate to, but that is changing. So in that sense, I want to draw your attention to two activities that are happening in the CS25 fixed large airplane world. And the first one is that we published a certification memo last year on this topic, modeling and simulation, focusing on CS25 structures. And that CM, and it's available on our website, so you can get it easily and read it, contains all the elements that I showed on the previous slides when it comes to credibility. So we really want to, I have published this document, not in the final stage yet, but as a draft, to draw the attention to the industry that if you're into this business of modeling and simulation, you better make sure, and there it happens again, that you do a credible job. Now, in the CS25 structures world, this is really gaining a lot of momentum, and that is the other thing I would like to highlight there. There is a working group active in this area that started basically a year ago, and that's also looking at the elements that I showed in terms of credibility, but they're going much further than the CERT memo. We are really trying to develop an industry standard that goes quite in depth in all of those elements, verification, validation, etc., but also trying to be practical and giving practical means to how to handle all these topics, because like I said, for example, errors and uncertainties, that's not an easy thing to do. So we're really pushing forward to produce a document, an industry standard that hopefully is useful, again, when you perform modeling and simulation. So those two activities are really in the CS25, but I think this is the point where I end my part of the presentation. I give the word to Laurent, and he will translate everything I said into the Rotorcraft world. Yeah, thank you.
Okay, so good afternoon. I am Laurent Pinsard. I am a senior structure expert at EASA, senior structure expert at CT2. So VIM is at CT1. CT1 is a large transport aircraft, and CT2 is Rotorcraft and a small aircraft. So I think the first, I have to move this. Yes. This second part of the presentation is probably to reconnect with the CS27-29 objective. But what has been explained by Vim is valid for CS25, large aircraft, but also CS29 and 27. 27 is small aircraft, small rotorcraft. But before moving to some examples which are going to be given to you, I would like just to briefly remind some specific feature for rotorcraft. Single load pass with catastrophic consequences. We have many parts like this on rotorcraft compared to large aircraft. What does it mean? Single load pass catastrophic. We have PAC's classification, which address under the fatigue issue, under 571 compliance requirements. And we have also specifically, which this does not exist, critical part, addressed specifically for the part on the rotorcraft with catastrophic consequence. And the purpose is to have a better control of the manufacturing process. So manufacturing process is one element to control on rotorcraft. So on larger craft, of course. We have also a design criteria for mechanical part. We do not design a mechanical part which is high fatigue loaded under static criteria. It is done under fatigue criteria with fatigue limit. So if we target, I don't know, on aluminium 400 MPa, here on the mechanical part, we will target far less than 100 MPa as a maximum stress to be in the part. Complex loading condition. It's about the same as before. We have rotating part with low and high cycle fatigue. We have also contact pressure, and I should say high contact pressure sometimes. We have fretting, we have torque application, and we have combination of all these conditions on the same part. We have also the flow tolerance evaluation, which is not done by crack propagation. It is done with other method. We have also, so as I mentioned before, complex manufacturing processes. Forging, so forging is also applicable to any aeronautical industry element, but we have also treatment with carburization, with high or tighten tolerances or severe tolerances, and we have complex assemblies. So I would like to say that based on this consideration, and in order to capture or to address this consideration, one of the preferred methods for compliance demonstration on rotorcraft is, of course, the test. But we have to keep in mind that the tests sometimes are not practically or physically possible to be performed easily. And so I would like to say that, yes, the preferred solution is the test, but the test, provided that the test is performed in a good condition and is realistic enough, because you can capture also all these problems of industry, of manufacturing, and so on. But I would like to say that it's not possible also to achieve certification without simulation. So to conclude, and I come to the same conclusion as him, we do not have to discuss anymore about the balance between simulation and test. We need simulation and test in order to go for to certify a rotorcraft. And both are necessary. So this is the first point. Now I will give you some example of what we do for modeling or simulation. I will start with airframe for static and fatigue strength with the general or the global finite element model, which is currently used in general for certification. I will just briefly remind what we are doing for mechanical part. Impact, we have seen nice bird impact before on the presentation. Fuel tank crash worthiness, ditching and flotation emergency condition, and I will finish with the rotor drive system. So first, airframe. One significant activity when we justify or we certify airframe, it is the construction of a global finite element model. However, I would like to mention that for static aspect, we have one requirement. We address also the fatigue under another requirement, and we make distinction between composite and metallic. Of course, what is also available for certification is the 29307, which is a proof of structure concept, which is also developed under 25 requirement. And we have, of course, this famous building block approach, which is well known. We start from coupon to component. And of course, here you can see that this is extracted from probably a large transport aircraft certification example, but you can replace the wing by the tail boom, or you replace the wing by the cabin, the complete cabin installation. But the principle is to go from the bottom of the at material level up to the full structure. So for airframe, what is done in terms of a global finite element model? And also, what is the objective? In fact, the objective for certification, we should say that it is to have a comprehensive understanding of how the loads, the stress, and at the end, how the margin, or how the loads and the stress are distributed inside the structure. So this is the purpose of a global finite element model. So the review which is done when we develop this global, or when the applicant develops this finite element model, is to ensure all the software selected, Knowing that we take the information, I would like to say. We do not investigate too much about, and in general, it is quite often the same software which is selected by any applicant, or very limited number of software are selected. We have also the modeling techniques, so we look at how the model has been built, constructed, and we check also the load application. For the validation process or logic, what is done in general, as I mentioned before, is we want to know where or how the load path is well distributed within the structure. If you install a spar, we want to be sure that the spar will work under a bending condition. If you have a boxes, we want to be sure that the box will work under torsion condition. And all these aspects are to be correlated with something. And for that, we have instrumented flight test, where the main frame, the engine frame, the main gearbox, the engine strut are instrumented, calibrated and instrumented. We have also airframe test, which is also another opportunity to correlate this global finite element model with some parameters like deformation, displacement, and also sometimes more sophisticated measurement. But what is interesting to see here is it's become a little bit conventional to do this correlation. We know now which parameter has to be recorded or measured and recorded, and we can establish quite a good correlation with this parameter between simulation and the test campaign, either flight test campaign or test static or fatigue test campaign. Okay. So this is I will say, a conventional activity for certification. We have about the same status for mechanical part. For mechanical part, in general, and because the loading is quite complex, we have instrumented part. The part is instrumented with strain gauges at the critical location, which is quite often determined by thanks to the simulation. So we calibrate these strain gauges. We fly the aircraft. We have a flight test campaign with the aircraft with this part instrumented and calibrated, and of course the correlation is done at this level. And during the test campaign, at the part level, we validate in general the static aspect, which are not a problem too much for the helicopter, and we validate the fatigue test. We validate the limitation associated to the fatigue test campaign. Okay, so I would like to say that global finite element model or mechanical part certification, the process is, I would say, quite a standard. We have some clear reference to establish the correlation between simulation and the test. And we know which parameter has to be controlled. I didn't mention all the other criteria which has been addressed by Wim, but we will see in the conclusion that it is probably one aspect which we have probably to improve a little bit the review of the simulation and to address probably more aspect in the validation of the simulation. Impact, bird impact. This is also quite a standard, I will say, simulation now. But the problem is, it is a dynamic correlation. So I'm always fear about when I see, and before moving to the detail, we have still some, it is still quite complex to correlate simulation and bird impact tests. We have still some, and recently we have some experience of bird penetration inside the structure when the simulation was showing the no penetration. So we can say, oh yes, but it was because of not the good selection of the material properties in the simulation or something like that. There is also always a good reason to explain why we do not correlate. But the problem is at the end, we didn't succeed first time. So what is, I will say, a little bit more complex compared to very basic standard static or fatigue correlation or simulation is, I will say, the parameter to be selected. When we do bird impact, one criteria, the pass-fail criteria for bird impact is no penetration. So this is quite easy This is quite easy to check, but what we want to check also is how the structure has been deformed. And we want to check is how realistic was the time of the peak of pressure and the shape at the time of the impact. And this is not systematically done. Means first the specimen tested is not systematically instrumented with, for example, pressure gauges or strain gauges. So it's make the correlation limited. We can see no penetration. We can make a general visual comparison between the two, the test and simulation, but we still have some issue to correlate with, I will say, a robust parameter for the correlation, because you can take also some pressure gauges and to try to compare. But what are you going to check? The peak of pressure, or the average of pressure? Is it similar? Because we are talking about the same level of MPa. What is the same level? So I would like to say that when we move to impact or dynamic test, the situation becomes a little bit more complex. Fuel tank crashworthiness. I just also want to mention that, because sometimes we discuss, do we need to simulate, do we need to test? Sometimes the rule does not allow you to discuss about test or simulation. When we have some requirement, drop test requirement must be drop tested. So no discussion at this level. But it does not mean that we do not need to do simulation. We need to do simulation. For example, in this case, it is the fuel tank drop test, the 15 meters high drop test. We need simulation in order to select the most critical tank. Or we select all the tank and we go for a drop test. Here also, what I want to say is the same problem as for the dynamic bird impact. We still have some problem to correlate with, I will say, a robust parameter. The requirement for fuel tank is quite severe. It's a 15-meter drop test with all the equipment installed on the blader or on the fuel tank installation, and with the surrounding structure. So we have always, at the moment, we do not succeed to fully correlate in general because of the complexity of the installation. We have problem to fully correlate this kind of requirement or this kind of test. And still the conclusion for that, it's that similarity to bird impact simulation, visual comparison can also support the correlation, but sometimes the pass-fail criteria here is no leak, no fuel leak. This is difficult. So we strongly rely on test. Ditching flotation, just to say that in general, we do not have, it's an example where the tests are not sufficient. Full-scale rotorcraft test for ditching is not part of the requirement. We do just ditching evaluation with pressure at the airframe level at time of ditching, and we have also some consideration for flotation time. And in this case, we do simulation, and we have some scale model test performed. And in this case, the correlation is done between simulation and scale model test, and then we extrapolate to the full-scale rotorcraft. So here it's an example where without simulation we will be very limited. Emergency condition. Here it's also interesting to see the difference between CS25 and CS2729. CS25 is requested, for example, some clear separation of the pylon or clear separation of the engine at the time of an emergency landing condition. For rotorcraft, we do not have this condition. So we have a very basic principle to say item should remain attached under IG level, IG load level, inertia loads. And also the only area where there is some dynamic test or dynamic evaluation to be performed is for seat. But because the configuration of a rotorcraft is quite simple and the seat configuration is limited, in general, we do not have to go to a dynamic simulation to do some selection of the seat to be tested. So we are not in the same, again, because of a product to be certified, we do not have exactly the same need in terms of simulation compared to larger craft. Rotor drive system. This is an interesting point, and it will be followed by the presentation by Sentient Science later. But rotor drive system, it will be included in the requirement for fatigue or damage tolerance. It will be requested to combine the effect of rolling contact fatigue, so the contact, at, for example, at the gear level, within the damage tolerance, or to address the rolling contact fatigue in the damage tolerance. In addition to that, it will be strongly recommended to have a fail-safe approach for the parts which are submitted to rolling contact fatigue. So we try to prevent the effect of rolling contact fatigue, and if it's happened, we will have some fail-safe capability to be demonstrated. And here we know that to perform a test in fail condition, in particular, for example, in a main gearbox, will be very challenging and is very challenging. So we rely probably strongly on simulation in order to, I will say, to support some tests, or to do some tests to support the simulation. But both will be necessary. And here, the challenging exercise is to address lots of, it will be, I will say, multiple factors, parameters, with condition for lubrication, temperature, geometry, material properties, heat treatment, and so on. So heat treatment at the gear level, which has to be well controlled. So here we can see that it will be a very high sophisticated simulation to be performed, and this will be presented later on. Here is just a summary of the situation for airframe mechanical part, impact, fuel-down crash. I would like to say again, airframe mechanical part, the process is well established. I will say it's conventional. However, as we have mentioned before, probably we need to go a little bit further in the investigation to validate or to accept the simulation. Impact and the fuel-down crash. I would like to say that we do not capture all the aspects within a dynamic simulation. And we have still some problem to well correlate and to fulfill the pass-fail criteria of the requirement. Ditching flotation, I mentioned that we do not rely on full-scale test, but we rely on the scale model test. And the simulation, of course. Emergency condition, we have a limited need in terms of simulation because we are talking about Rotorcraft. And rotor drive system is probably at the moment, it will be the next real challenge to develop a robust simulation to simulate and to help for compliance with the rotor drive system. So again, here it's a summary of my personal conclusion for this presentation. It's probably, yes, we need validation is quite well established when we know how to correlate when the parameter has been identified. However, we need to make progress in terms of extrapolation, error and uncertainties, governance, experience, and verification. For example, to know exactly what is the limit of your simulation. Can you increase the weight of the rotorcraft by 1 ton or 2 tons if with the same simulation techniques? This is not really detailed at the moment in certification process. And again, both simulation and test help us to have I would say, comprehensive understanding of a structure, how the structure will work in terms of load path or stress, and at the end to derive or to obtain the proper margin and to justify a proper margin on fatigue, static, or any other criteria which are addressed on the certification. Thank you. So now I leave Vince to do the final conclusion.
So just to wrap things up, what we've shown you in the showing fully realize that the same thing happens in flight tests. These within EASA, which define synergies in different, and also look when it comes to structure with the same question. So there's definitely some work to be done. We see this trend, and I think safety point of view, we see the benefit. Better, reliable product. From a safety point of view, we also see the benefits of things analytically, physically testing. However, credibility is key. And we think you better make job and consider what we said is happening in the school.
Sorry to interrupt. I don't know if it's just me or, but I have really hard time hearing you.
Sorry. Okay, sorry for that. I was stepping away from the camera. So,
all right, thanks. Way better, thanks.
Okay. So just to briefly summarize, we see an increase in the use of analytical techniques. We see it as an opportunity to not only build better but also safer products. But credibility is key to the modeling and simulation efforts. And this thing keeps shifting. Okay, some built-in time delay perhaps. So within CS25, that's definitely recognized and being worked at. And I'm sure within the Rotorcraft community, you're also aware of this. So we talked about CS25, but a lot of it applies to you as well within the Rotorcraft world. And we talked some example applications by Laurent showing again that you need this mix of test and simulation. And it really depends, I think, on the case and where you are as a company, where you're comfortable with. Maybe some companies I know are more comfortable with the physical testing where possible, and others want to go to more advanced analysis. So it's a choice case by case and company by company. So again, that wraps up our presentation. And if you have any questions, we're happy to answer them.
There are questions.
Yes, Giuseppe Strazzini from Leonardo Helicopters. May I ask a question?
Yeah.
Okay, so the question is fairly simple. Is EASA considering or planning for accepting also data-driven model for justification for certification, or when you are talking about simulation, we are still relying heavily on physics modeling and simulation? Thanks.
So, okay. So when you say data-driven simulation, you mean in the direction of machine learning?
That's correct.
Yeah. Well, I think the question about artificial intelligence has been raised during one of the previous presentations, and I can only speak for myself, but it's a big unknown for us. We have the roadmap that was mentioned, the EASA roadmap, I should say. But where it all ends in terms of modeling and simulation, I really don't know. We are connecting to different communities that are looking at it. I think we are still far away from a system that automatically, so to speak, can design something for you and make sure it works and is reliable enough. So what I see at the moment, the machine learning tools that are being used are still at a relatively low level, are helping the analyst to make certain decisions. But again, we are far away from an automated process where you can step away and let the computer do everything. So we're keeping an eye on it. There are several working groups from NAFEMS and ASME that are looking at it, and you probably know that. But again, my impression is it's still early days, unless you have more information. But
No, you asked my question. Yeah, basically, yeah, I know very well. So we are actually working on that. But so far, what I've seen from EASA is a tendency to work across implementation of these techniques in for a system, airborne system, but with not like a defined a dedicated scope on simulation and certification. So what comes before in terms of how can we apply those techniques in order to, for example, save flight testing, extrapolate information that we didn't specifically tested, but where a machine learning technique might have learned from the test that we actually already did. So everything that relates to maximize the value from the data that we gather rather than creating new data from scratch. So that is what I have seen is not so it's not worked out in EASA, which is actually working towards implementing those techniques for added functionality in avionics, for example.
You're partially mostly on airborne systems and pilot interaction, but we do have a small paragraph in the roadmap that talks about design and manufacturing in relation to, well, machine learning, artificial intelligence. So we don't lose sight of it, but like I said, it's early days and yeah, it's too early to say something.
Okay. All right. Thanks a lot. Thank you very much.
There is a question on the chat. You can read it.
Yeah, please.
Gareth, can you specify the finite element model method to be used?
The short answer is no. It's up to, well, the applicant, the company, to choose a software tool, whether it's Nostron or Abacus or LS-DYNA, whatever you want to use. The code verification question is on the table. At the moment, we are not too worried about those commercially available software tools. They are used widely, and if there are real problems, they are discovered typically. In-house developed software tools, we think we should spend more time on code verification to make sure about the quality of the software, but that's a challenging process. But apart from that, to answer your question, no, any company or applicant is free to use whatever software it wants, but depending on what type of software and how it is being used, you may have to show certain quality assurance and make sure that the software tool is reliable enough and accurate.
We have some example in the ASP material, guidance material, where some name of software are presented.
Okay. Other questions? No? Thank you very much.